All right, hello everybody. Welcome back to Statistics for Linguistics. Today we are back in the office because it's a cold and slightly snowy Saturday morning. But that's okay because we're going to talk about conditional probability today. And I'm hoping to make this just kind of a relatively short and focused lecture, although there are a couple of things I wanted to talk about which were kind of leftovers from the last lecture on binomial distributions. And one of those is this video, which I believe we've seen before a long time ago, but I wanted to kind of take a look at again. So this is a guy from the University of Cambridge Science Festival who has this unusual device, which is called a quincunx. And so all he does here is pour a whole bunch of marbles down into this kind of filter, I guess you could say. And at each spot in these various levels in the filter, the balls have to kind of make a decision to go right or left, or they wind up going right or left, I guess you could say, because they're not doing this thoughtfully. But be that as it may, there's just a kind of a series of individual decisions that get made to determine the pathway of these balls. And at the bottom of it all, don't stop, it winds up forming this distribution, which looks like a normal distribution, but we now know is a binomial distribution, because this is exactly the same way that a binomial distribution was getting made with our little examples last time that we were running just through R. It's nice to see the whole thing flesh out once you get a few hundred little marbles in there. Just one point I kind of wanted to make here, as we see the last little balls go down to their fate. Thank you very much, James. We'll get to the tail end of this. This is not a perfectly, the pattern you get at the end is not a perfectly normal, or it's not a perfectly binomial distribution here, because it's not sort of artificially or theoretically generated, right? So those patterns we were seeing before in the last lecture, we could just kind of determine the probability and say what comes out of that, right? And we get this sort of theoretical pattern, which is painted on here in this gray line. But since this is an actual sort of instantiation of sending these balls through these pathways, we're going to get some random noise or variation in the actual output. And in this case, you see like this little bar over here on the left-hand side is a little bit higher than this one, even though they're supposed to be the same height, that sort of thing. So it's not going to be a perfect depiction of what the abstract theory says it's supposed to be, right? And so that kind of gets into that issue of the two different probabilities I was talking about last time, hopefully not too confusingly, when I was talking about the output of the results of a binomial test. So like in theory, you can say if, at each one of these points in these pathways, the ball has a perfectly 50-50 chance of going one way or the other, we can expect this sort of pattern of a gray line here. And then you can actually run the experiment and find out what you get. And in this case, we see that the pattern formed by the ball stacks, I guess you could say, is a little bit different from that gray line. But that second p-value, the p-value that we get from the binomial test, kind of tells us the probability that of the actual observations being significantly different from the theoretical or the sort of proposed probability, as it were. And in this case, it doesn't look like it's that significantly different, the two of them, the observations and the theory. But that's what that sort of secondary p-value represents, or the output of the hypothesis test represents, is whether the observations are so significantly different from our initial hypothesis that we should change that initial hypothesis. Because we don't know, like we're just assuming at each point here, there's an equally there's a 50-50 chance the ball might go either way, but some of these might not be operating the way they want them to, or what have you. So by running the test, we can see whether we get sort of the output we expect. And in this case, basically, yeah, it looks like that's the case, but maybe one of these is a little bit off, or if there are a whole bunch of them that are a little bit off, instead of having a 50-50 chance of going either way, you have like a 1/3 chance of going to the left and a 2/3 chance of going to the right. You'd see a different pattern forming down here, like we saw with our different binomial distributions down like at the end of the previous lecture. So the the sort of probability that matters for forming this distribution is the probability of going one way or the other in these different choices or these different pathways. And then that other little p we get from the hypothesis test just tells us sort of the probability of how well the observations match up with our sort of initial theory about how this should work. So hopefully I haven't talked about that too many times that you're totally confused, but be that as it may, I'm just going to move on anyways, and also kind of address something else I thought about after walking through the lecture notes last time, which again, if you're a baseball fan, it's going to mean something to you, but it also matters to just how we run stats and linguistics or whatever else as well. But I was running this binomial test where I said, well, let's say we do have one of those setups where there's a 1/3 chance that the output could go one way, like to the vowels, and a 2/3 chance it could go the other way, like to a consonant. This is kind of a typical ratio you would get in baseball as well, for there's a 1/3 chance you'd get a base hit and a 2/3 chance that you would not do well on your at bat as a batter. But if you get one success out of 5 in that scenario, or one vowel out of 5 tiles in a Scrabble game, something like that, it's not, in any obvious way significantly different from an underlying probability of 1/3, because this p-value says that there's a 0.46 chance of that happening anyways. This is, not your best day in life, but it's not indicating that you're sort of not as good as you think you are, I guess is the easiest way to put it. And what was kind of funny about that is that, this is, in a given baseball game, you get 5 at-bats is a typical thing you can expect, especially if your team's doing pretty well. But the funny thing that happened was that kind of unexpectedly, I tried this with an 8 out of 40 sort of success rate. So if you had 40 at-bats and you got 8 base hits, and you still thought that your underlying batting average was 1/3 or 0.333, whatever, does that still fit? And the ratio is still the same. It's 1 out of 5. And this is 8 out of 40. So 1 out of 5 would be a batting average of 200 or 0.2 basically, which was traditionally known as the Mendoza line, which is kind of like the line at which you go from being a not good batter to a really bad batter. Anyways, the point is that even though this is the same ratio, then we get a different p-value because we have more observations. So before, the p-value here said that, okay, this is just a bad day. You're still a good hitter, or you're still going to assume that this underlying probability of 1/3 holds for this data set. But when you get more and more data, you find out that, this hypothesis doesn't really fit. Even though you're getting the same ratio, with more data, we can see that the output is not sort of matching up with the underlying hypothesis. So here, the p-value is less than 0.05. And I kind of just walked into this unknowingly, but I'm glad that I did. I said, again, not to dwell too much on the sport of baseball, but when I was a kid, there was, people would report a lot of numbers in the game because it just generates a lot of numbers, but they weren't super sophisticated about what they meant. And nowadays, you hear, if you watch a game, like, he's 1 out of 5 today, but that's a small sample size. You looked at a batter and they were 8 out of 40, 8 successes out of 40 tries. Then you'd say, well, that's a big enough sample size for us to say that he's not doing very well. And the same thing kind of holds true for linguistics, right? So you don't want to have a very small, I guess this has also changed a little bit since I was younger in linguistics, but you can go back and read studies from the way back days, like the 50s and the 60s, or even say in the 80s and 90s when I was coming through the system, where people would get data from like 1 or 2 speakers of a language and say, okay, here it is. This is the pattern that we get from the language. We've shown that it exists. Nowadays, people get more data, right? And they actually run experiments in linguistics as well. That's changed too. So they're getting more data and more reliable information about whether sort of these underlying hypotheses hold water. So watch out for that, the sort of small sample size problem. There's also, I think, a large sample size problem that you could run into, where if, instead of running 5 trials or 40 trials, you might run like 400 or 4,000 trials, and then you're almost guaranteed to get a significant effect. But that's less likely. You're less likely to run into that because we just don't have the resources often in linguistics, and we don't have the time. in baseball, there's way too much time. You do get thousands and thousands of trials, but I won't get into that. I'll just say that usually the more data you can get, the better. And if anything, you want to kind of stay away from very, very small numbers. And we'll see that again as we start walking through conditional probabilities, and especially in something called chi-squared tests, which is where we're kind of leading up to next. Okay, enough diversions to start off this lecture. What I want to do today is go back to our little D&D game. The dice are back in their home in the little plastic bag on my desk in my office here. But what we're going to do is change the rules a bit. We're not actually going to roll any of the dice. And they'll say that before we had an elf playing with these rules for its dice rolls on its turn. The elf would roll a d20 for its attack roll. Might as well break it out while I'm walking you through this. And then on any roll greater than 15, the orc would be hit. I just rolled a 13, oh well. But if the roll is greater than 15, then the elf would roll the d10 for damage. And then the orc would lose some hit points. Let's say on this particular roll, I got a 4. So yeah, that was the way it started out. But I want to play with a set of additional rules now. I'm not actually going to play this. We're just going to think about it. So we'll say that for any attack roll of 18 or 19, the elf will add 1 to its damage roll. 1 hit point, that is. And then for any attack roll of 20, the elf will add 2 hit points to the damage roll. Yeah, so this is going to change our calculus a little bit. How is this going to make an effect on the game? With our old rules in place, we could ask, what is the probability that the elf would inflict damages of more than 5 hit points on the orc on any given turn? I'll let you think about that for a second. But remember, we have a d20 in play, and we have a d10 in play. What probabilities do we have to consider to answer this question? Well, there's 2 different events. The elf would hit the orc with a probability of 1 out of 4. Anytime you roll greater than 15 with one of these guys out of 20. And then secondly, the elf would get 5 hit points, would get more than 5 hit points of damage with a probability of 1 out of 2. I'm going to kind of fix this because I just realized it's not just 5, more than 5 hit points of damage with a roll of probability 1 out of 2, because rolling a d10, you get greater than 5. 1 out of half the time, basically a 1 out of 2 chance of that. So the probability of getting more than 5 hit points on any turn is 1 out of 4, the probability for this first roll, times 1 out of 2, which is the probability for the second roll. These are independent events, so you just use the product rule and multiply their probabilities by each other to get the overall probability of 1 out of 8. So on 8 different turns, you'd expect to see more than 5 hit points of damage on the orc 1 out of 8 times, assuming the elf has survived that long, right? Okay, what is the probability with the new rules in place? And just to remind you, the new rules we've got going here just apply to these high attack rolls of 18 or 19. You add 1 to the damage roll. For an attack roll of 20, you add 2 to the damage roll. Okay, so the way to figure this out is to use the product and sum rules. But we have more sort of contingencies to worry about. So we can roll a 20. Let's see if there it is. 20. We can roll a 20, 1 out of 20 chances with this guy. And then when we do, we're going to get more than 5 hit points on 7 out of the 10 rolls that we'd have with this guy, the D10, right? So if I roll a 5, I'm adding 2 to that, so I get 7 total hit points of damage. If I roll a 4, then I get 6 total hit points of damage. So anything above a 3 will give me more than 5 hit points of damage in this new scenario. So my combined probability of getting greater than 5 hit points when I roll a 20 on the attack roll is 1 out of 20 times 7 out of 10, right? So that, or 7 out of 200, I guess you can say. It's just funny, I was listening to myself say the word 20 very clearly. It's not 20, it's 20. Anyways, for the rolls of 18 or 19, there's a 1 out of 10 chance you'll get a roll of 18 or 19 because there's 2 chances out of 20, basically. And after you roll those, you have a 6 out of 10 chance of getting more than 5 hit points on the damage roll because you're adding 1 to it. So anything from 5 to 10, that's 6 out of 10 total. And then you multiply those together and then add the last 2 possibilities, which are a roll of 15 or 16, a roll of 16 or 17 will also inflict damage on the orc, but that's the old rules of just roll the d10 without adding anything to it. So you get 1 out of 10 times 5 out of 10. Overall, we get 7 out of 200 for this first scenario, 6 out of 100 for the second set, and then 5 out of 100 for this last set. Those are mutually exclusive events, so we add their probabilities together and we get a total of 29 over 200. Yeah, so before we were at a probability of 1 out of 8, which converts to 25 out of 200. Now we're doing a little bit better as the elf, and we have a probability of 29 out of 200 that we'd inflict more than 5 hit points of damage on the orc. So that's better for the elf, not the orc, but we don't like the orc anyways because the orc just keeps winning, and that's no fun. All right, so hopefully that makes sense. The big moral of the story is that this scenario involves a case of what's called conditional probability, maybe in a different way than you've ever thought about it before. I don't know. But basically what this means is that the probability that the elf will inflict more than 5 hit points of damage on the orc depends on the elf's attack roll. So the damage and the attack roll values are no longer strictly independent from one another. There's a connection between the two. Before, we were just rolling them separately, and we could multiply their probabilities by each other for that reason. But now we have to consider the value of one when we're calculating the value of the other. That's conditional probability. Okay, so here's the way conditional probability rules are formalized. So mathematically speaking, this is going to use a notation which you may have seen before somewhere down the line. But this is read as the probability of B given A. So it's just this vertical line in between the two. It's on your keyboard there right below the delete key. Anyways, it's probability of B given A equals the probability of A and B occurring together divided by the probability of A. And you can actually express this in a different way if you just multiply both sides by what's in the denominator here. You get the probability of A and B equals the probability of A times the probability of B given A, for whatever that's worth. What we can start with this here, and then we'll use this later to kind of convert it into something else. But this is the basic definition of what conditional probability is, or how you determine it for these two events, A and B. Yeah, so note, basic idea here is that the probability of B happening is going to depend on A in some way, right? And that dependence relationship is kind of the crucial part of this, because we've seen that before when we're doing linear regression or analysis of variance, that sort of thing. Eventually, we will be able to use this to kind of develop a model where B will be dependent on A in some fashion. If B and A are independent, we've seen that before, that the probability of A and B is just the probability of A times the probability of B. But now we add this new twist in it where B depends on A to some extent. Okay, this is what I just said, but what the independence scenario implies is basically the occurrence of A has no effect on the occurrence of B. The sort of conditional or dependent scenario implies that the occurrence of A does have some effect on the occurrence of B, and that's what we're going to try to figure out how to quantify, basically. From the other point of view, if A depends on B in some way, then the probability of A given B equals the probability of A and B, the two of them occurring together, divided by the probability of B. So we can make the same sort of transformation with this and say the probability of A and B equals the probability of B times the probability of A given B. Okay, that looks almost identical to what we saw before, except we're switching the order of the variables. But what this means is that we can take this one, this probability of A and B, which is this probability of A times probability of B given A, and say, well, that's got to be equal to this, the probability of B times the probability of A given B. So now we can equate these two, and I'm not going to read through them all again because that takes a while and you've heard it enough times already. But what I'm going to do is divide both sides of this equation by the probability of B. And instead of having an expression that looks like this, where you have the probability of A and B together on the top of the fraction, I'm going to convert that into this bit here. So the probability of A given B equals the probability of A times the probability of B given A divided by the probability of B. Okay, so what, you say? And it turns out this actually has a lot of implications because it was discovered by this guy named Thomas Bayes. And here's a picture of somebody who's claimed to be Thomas Bayes in Wikipedia. But yeah, the funny little story with that is that if you read the footnote on this picture in Wikipedia, is that it says it's probably not Thomas Bayes. It just comes from a book it was made in like 1936, which is like 200 years after this guy lived. He was like a Presbyterian cleric in the UK somewhere who, I guess when he wasn't preaching to the faithful, just played around with probability in his spare time. And he came up with this famous equation, which is known as Bayes' theorem. And the coda to the story about this picture is like, well, this is the only known picture that's claimed to be Thomas Bayes, and it came 200 years after he lived, so it's probably not him. But it's funny to think of probability theory when you're trying to depict who Thomas Bayes was, because yeah, like I said, he wasn't like a professional mathematician or something like that. He was a minister, but his huge influence on the world was through this theorem. And it's interesting. We can't like dive into this nearly as much as we probably should given our time constraints in this class, but people use this theorem, this sort of simple looking combination of probabilities, to do all sorts of amazing modeling things in the modern world. And it kind of actually is a way to do a whole different sort of statistics than what we've been doing up until now in this class. So what we've been doing until now is generally referred to as frequentist statistics. And it kind of focuses mostly on that sort of null hypothesis significance testing paradigm, where we're trying to like figure out whether, our null hypothesis is true or not. And you can contrast that with Bayesian statistics, which kind of don't reach those sorts of definitive conclusions about what you can infer from your data, and instead it kind of comes up with like probabilistic conclusions about what you can learn from your data, where you say, instead of having a null hypothesis, you have priors. So a kind of set of beliefs about, what the underlying parameters might be in a particular situation. You collect some data, see how well that matches up. And then you don't sort of accept or reject your priors. You sort of just adjust them and say, knowing what I know now, I'm going to just kind of move these in a slightly different direction to make them more accurate with the data that I've observed. So I guess in a sense it's more forgiving that way, but it's also maybe less satisfying that you don't reach this definitive conclusion. But by the same time, by the same token, you might avoid the problem of all those false alarms that we get in modern day statistics because you're just not reaching those like final conclusions. Anyways, there's more to Bayesian statistics than that, but what I want to do here for the moment is kind of show you basically how this works in terms of calculating these probabilities, because as the IPS textbook itself says, it's far better to think your way through example problems rather than memorize these formal expressions, because the first time you look at Bayes' theorem, you're like, it's a lot of variables and stuff I haven't seen before. So let's try some examples, and then I'll go back to sort of the bigger picture implications of this whole setup. So just to show you kind of how to use this notation for this setup that we were talking about a minute ago, you can say come up with different calculations of probability for, say, damage rolls or number of hit points you get out of the damage roll in our Dungeons and Dragons setup, given certain results of your attack roll. So the probability of the hit points being greater than 5, given an attack roll of 20, is 7 out of 10. And I'm trying to be kind of careful with my notation here because we're using this D10 to roll for damage, but it's not like I got a 3 there, right? So that's a very convenient example. So for 3, we add 2 to that and we get a total of 5. Or if I would have gotten a 4, then I would add 2 to that and get a 6. So it's not about the probability changing of the roll itself. It's the probability of the sort of overall outcome because I'm adding 2 to this roll. So that's why I'm calling this hit points here. But the probability of the hit points being greater than 5 when my attack is equal to 20 is 7 out of 10. But that's conditional. So the probability of the hit points being greater than 5 when the attack roll is 18 is just 6 out of 10, so on and so forth. When the attack is 16, it's just 5 out of 10. So this outcome depends on the outcome of the initial roll. So with that in mind, for our upgraded ELF, what is the probability of the attack being 20 when the hit points are greater than 5? So this is kind of where Bayesian statistics becomes fun, is that you can kind of like go backwards in time with them. So to a certain extent, we've set up a scenario here where we change the conditions and has different sort of outcomes on the basis of those changes of conditions. But here we're going to look at the outcomes and try to figure out what the conditions were for that, basically. And we can do this with Bayes' theorem. So this is sort of like a scenario where you have friends who have invited you to play a Dungeons and Dragons game, and you get there a little bit late and you miss that first round of rolling, and you find out that after that first round, the elf has like taken 7 hit points off of the orc, and you don't know what happened with the rolls at all. But you want to figure out, well, maybe what happened there is that the elf rolled a 20 with these rules, and I want to figure out what is the probability that that actually happened. You can do that knowing the rules of the game in general. So we're going to try to answer this question by starting with Bayes' theorem. Sorry, my setup reminded me of that episode of Community where Donald Glover goes out to get the pizzas and comes back and the whole world is blown up. Sorry, maybe I'll show you that video next time. Anyways, right, we can calculate this using Bayes' theorem, and this is the setup we're going to use. So the A event is going to be attack equals 20, rolling a 20 on that attack roll. The B event is going to be the hit points are greater than 5. And it's kind of nice to put them in this order because that's kind of the order in which they happen in reality. But to figure this out, we need to sort of separate these probabilities. So the probability of an attack being 20, just in general, is 1 out of 20. And then the probability of hit points being greater than 5, just in general, is going to be what we calculated before. Also, we calculated before the probability of hit points being greater than 5 given this attack of 20 is going to be 7 out of 10, right? So because we're adding 2 to this value when the attack is at 20, we get 7 out of 10 probability for HP being greater than 5 in that scenario. We calculated this overall probability of the hit points being greater than 5. It's 29 over 200. We just plop these numbers down into this equation, and we see as we sort of calculate these things out, on the top it's going to be 1 times 7 is 7. On the bottom of that top half, it's 20 times 10 equals 200. So this winds up being 7 over 200 divided by 29 over 200. You can simplify that fraction and say it's 7 out of 29. And this is maybe kind of a convenient sort of scenario to use as well to see how this works. So if I go back to our initial calculations before we met Thomas Bayes, right, so we have like 7 out of 200 plus 6 out of 100 plus 5 out of 100. That gives us an overall probability of 29 out of 200 for getting more than 5 hit points of damage in this particular case. 7 of those sort of 29 chances come from this first scenario of rolling a 20 on the attack roll. So you can kind of think of it like that. It gets you into the same place at the end. But that's the probability, and that's how it would look using Bayes' theorem in this particular case. Okay, I'm going to take a brief break, and I'm back. Okay, so what's fun about this is that Bayes' theorem can kind of help you look back and forth in time, right? So we saw the outcome in that last scenario. We wanted to figure out what were the possible causes of that outcome. So to put it another way, this can help us understand not just the effects of certain causes, but what causes may have produced certain effects. And like the one sort of scenario you can think of this being useful in the world of linguistics is, say, trying to figure out what's going on in the phonetics versus phonology split. So in the phonetics world, we get all these observations of surface details, like the VOT of a particular stop, or the F0 or the F1 of a different vowel, that sort of thing. So we know we can run experiments scientifically and get people to produce a whole bunch of P's and T's and K's and say, well, if a P is aspirated, what is the likelihood that it has 40 milliseconds of VOT? And then, you find out a certain probability for that. But you don't really have the luxury of being able to run those experiments in normal life. Instead, you just hear people speak or say things, and then you have to figure out what sort of was underlying the things that actually came out of their mouth. So Bayesian analysis can help you answer questions like, well, if a stop has 40 milliseconds of EOT, what is the likelihood that it is a P rather than something else, right? So this is kind of a Q for some underlying category in the system. And it may be a different stop, it may be a P, and maybe whatever. But this is at least like an outcome, something you can measure to try to figure out what these sort of conditions were that produced that outcome. Another sort of situation, I don't know if I want to get into this, but I will anyways, because the phonologist in our program, Darren Flynn, I'm the phonetician, so why not? The phonologist in our program, Darren Flynn, was telling me about this the other day, about people being hesitant to get the vaccine for COVID, that sort of thing. And they were saying like, oh, like, 50% of the people in the hospital are vaccinated. 50% of the people with COVID in the hospital are vaccinated. So like, it's just kind of a toss up, whether you're going to get the disease or not. That's not a great way to look at it, as hopefully you can understand, right? So you can think of the question sort of in a Bayesian sense. In the straightforward sense, that you can measure like, well, if you're vaccinated, what is the likelihood that you will get hospitalized due to COVID? And it's probably not good. Actually, I didn't come up with the right numbers for that. But the sort of Bayesian question you can ask is like, if you're hospitalized with COVID, what's the likelihood you got vaccinated or not? And there is some relevant data for that here on the Alberta COVID-19 website. So in terms of just overall cases, so I guess first of all, I should say, where'd it go? Yes, vaccinations. We're doing great with vaccinations at this point, which is hopefully why we're doing better with the virus overall. But 88.6% of the population has received at least one dose, at least if they're over the age of 12, and now the kids are getting it too. So a lot in the overall population, 3/4 have gotten vaccinated. But if you look at who's getting sick, only 44% of the people are getting vaccinated, or 44% of vaccinated people are getting cases. The number is slightly higher for the unvaccinated, even though there's far fewer of those people, right? It's like a 3-to-1 ratio. And if you look at the hospitalizations, it's almost the other way around. So it's almost like 1 out of 4 hospitalizations are from vaccinated people. And, well, not quite 3 out of 4 are from unvaccinated people. So even though there's a much smaller proportion of these people out there, there's a much higher proportion of them in the hospital. So, yeah, if somebody's in the hospital due to COVID, you can kind of infer it's likely that they're not vaccinated. That's sort of a Bayesian way to look at it. The sort of more feed-forward way to look at it is like, if you're vaccinated, you're less likely to go into the hospital, right? So, yeah, that's kind of the sort of flip you have to make in your mind to see where this can become useful. And I guess I'll say just overall, again, getting vaccinated is useful for a wide variety of reasons, but hopefully you already know that. Anyways, reverse predictability. I want to look at another example, which, I don't know, could be equally as controversial as getting vaccinated. But I want to use this concept of conditional probability to analyze a very simple example of race and poverty in America. And so these are numbers that come from a little more than 10 years ago. They come from the 2009 U.S. Census. I used them the first time I taught this class. And they're interesting for a variety of reasons, so I haven't updated them. But yeah, in case you're not familiar with my home country, the United States of America, there's a bit of a race issue there, and has been for some time. So we can quantify this in a particular way, looking at how many people of different races are living under the poverty line. This is what they did with the 2009 census data. So these are numbers in millions. And overall in the U.S. at the time, there were 53.8 million people living under the poverty line. And 1.7 of them were Asian, 9.9 were Black, 12.4 were Hispanic, and 29.8 million were white. Sorry, I don't have the numbers for the indigenous people of the U.S. Unfortunately, as often is the case, they get left out of the equation. Not for better, but that's what those whole land acknowledgements are about in part. Anyways, be that as it may, we can also look at the overall numbers of people in these groups. So there are these numbers like 13 million Asian people, 38 million black people, 49 million Hispanic, 242 million white people in America at the time. So we can think of conditional probability in kind of a very simple way here, which hopefully would make intuitive sense. So you can look at it as like the probability of being in poverty given a certain race. And for that, you can kind of just, what you kind of do is just divide this number by that number. So the total number of like Asian people in America is 13.6. The total number of Asian people in poverty was 1.7. So you divide 1.7 by 13.6 and you get this number. And unfortunately, I'm kind of, now that I'm looking at this, I'm kind of thinking I should change where the dots are because I'm getting percentages here rather than like probabilities. So this might make it a little bit clearer what I'm trying to do, because if I don't do that, it starts to look like I'm telling you millions of people here rather than probabilities. So there is a basically 1 out of 8 chance if you're Asian that you'll be living under the poverty line. And that goes to about 1 out of 4 if you're black or Hispanic, and it's about 1 out of 8 as well if you're a white person. So overall, for everybody, it's a little bit higher than 1 out of 8, maybe more like 1 out of 7, 1 out of 6, that sort of thing, because you got to balance out across these 4 different groups. But you can think of this as the probability of being in poverty given a certain race, right? So kind of the underlying question here, I just alluded to there being a race issue in America. So ultimately you ask this question like, well, does your race affect your likelihood of being in poverty in the US, right? You may already have an answer to that question in your head, but we can kind of walk through it quantitatively here. So we've already talked about that, and I'm going to switch these again. And I'm sorry about this for doing this on the fly, but I think it'll make it clearer by the time I post this. So I'm going to convert these as well for the row beneath it. The next row looks at what is the probability just that you are a certain race in America, independent of the whole poverty issue. And so only basically what this is saying is that only 4% of the people in America are Asian. That's what this 0.04 means here. So to get that, just dividing 13.6 divided by 343.3. So, it's a relatively small total, 1 out of 25. The numbers get bigger as we move to the right in this little chart. So 11.2% of people are black, 14.3% are Hispanic, and the majority, 70%, are white. Again, going back to the old days in my mind, since I've been talking about those so much, I didn't learn this fact about the U.S. until I was like in high school. I think up until that point, I always thought like the country split to like maybe like 60% white and 40% black, something like that. Like, no, it's like pretty consistently about 1 out of 8 people are black still since that time. So that number was smaller than I thought it was. And this number, the overall percentage of white people, is kind of well known to be going down, but at this point was at 70%. So still a majority, and that's going to have an effect on this kind of overall analysis that we get at the end of this. So we can calculate based on these probabilities what the expected numbers we should get are in each row of this table, or each little cell of this table. All right, apologies for the break there, but I had confused myself, so I wanted to make sure I wasn't telling you something wrong. But what we want to do here is for this expected row of data, we're going to take the overall total number of people in the US and multiply that by the probability of being in poverty, which is that right there. So just to show you the way I calculated that, there's 53.8 million people in poverty in the US. Divide that by the overall number, 343.3, you get a probability of 0.157. So I can take the total number of people in the US, and there's going to be some rounding off here a little bit, but multiply that by the probability of being in poverty in general, and then also multiply that by the probability of being a particular race. So let's take Asian people here. So it's 0.04 probability and multiply that, and we get basically 2.1. So there's a little bit of rounding here, so we'll just kind of ignore some of the details, but that's where these numbers are coming from. And we start out with this table up here with the actual number of people in poverty. So remember, again, this is sort of like coming up with a theoretical model for how this should work, and then actually looking at the observations and seeing how well they match. The expected numbers are here. The actual numbers are here. The difference between the two, well, there's not going to be a difference for the overall numbers, but we are going to ignore those for the time being. The difference is going to be this. So we'll take 1.7. This is our observation, how many Asian people are in poverty. This is kind of the expectation we'd have if these two things were independent, poverty and race, and we get a difference there of negative 0.4. So the other ones, this is going to be 9.9 minus 6 for black people. That leaves us with a difference of 3.9. So on and so forth for the other two groups as well. And basically what we get here is a little bit of deviation from 0 on the positive side there, on the negative side there. Basically trying to see how well this row matches up with this row. Okay, right. So we're going to ultimately use this as another way to kind of generate a hypothesis test, but just in a slightly different way. Remember I said kind of the interesting question you can start to ask with conditional probability is whether there's a dependence of one event on the other. And in this case, we're developing a model where there's no dependence between these two things. And then this is going to give us a way to quantify how well reality matches up with a world where poverty and race are not dependent on each other in the US. Before I get into that, though, I'll just kind of reiterate a couple of interesting facts about this data to begin with. So first of all, if a person is white, what is the likelihood that they are in poverty in the US in this data? And that answer is 12.3%, which, if you go back up here, is going to be the lowest number out of these four groups. And then if we go back to the second question, if a person is in poverty, what is the likelihood that they are white? And the answer there is 55.4%. So it turns out that the funny little paradox is the ethnic group in America that's least likely to be in poverty is white people. And that, you could use that to substantiate claims of what is called white privilege. And then at the same time, the majority of poor people in America are white people. And, that can feed into a sense of white victimization. So, yeah, that's a little bit weird. And just to clarify, because people have gotten confused about this in the past, but both of these statements are true. So the ethnic group in America that's least likely to be in poverty is white people. That's this 12.3% number here. And that's just based on this data, this conditional data. So the likelihood of being in poverty based on the fact that you're white is the smallest number out of all four of these groups. And then also this other fact is true as well. The majority of poor people in America are white, and that's primarily based on the fact that a sizable majority of people in America are white, or at least were in 2009, right? So the ethnic group that's least likely to be in poverty is white people, at least in terms of any individual being in poverty based on their race. That's how it works. At the same time, the majority of poor people in America are white people. So that's kind of looking at it the other way around. Given your race, what is the likelihood that you're in poverty? That's a very small number if you're white. Given the fact that you're in poverty, what is the likelihood that you're white? That's a very large number, kind of working the opposite way. So I have this joke, which I came up with 2 years ago, about do these seemingly incommensurate facts help account for the political rise of Donald Trump? I'll leave that as an exercise for you to solve at home because I'm tired of thinking about Donald Trump. And we'll just move on and just say thanks that we're in a new administration. For better or for worse. Anyways, looking back at the table up above, the observed minus expected total is -8. How do we know whether this or not this is meaningfully different from what we'd expect? And we're going to determine that by running something called a chi-squared test. And that is what is going to be the focus of the next lecture. So I'm going to pause here. Like I said, I wanted to make this relatively short and sweet. Don't know if I succeeded. But anyways, chi-squared tests are going to be useful. We're going to be able to add them to our toolkit because they come into play in a new sort of scenario for our data. And we can use them when our independent variables are categorical and when our dependent variables are categorical as well, which is a scenario we haven't seen before. We'll also talk next time a little bit about something called proportion tests, which are closely related to chi-square tests, and also the binomial distribution. So stay tuned for that, and we'll get deeper into this as we go. See you then.